In this video, we're looking at the relationship between two categorical variables again, but this time we're going to be using a theory-based approach. So this was a study sponsored by General Motors to help employees stop smoking. In the study, half of the 878 volunteers were randomly assigned to receive up to $750 if they quit smoking. So this is the treatment. It was like a financial incentive for them to quit. So that's our treatment group. And then the other half were just encouraged to use traditional methods to quit. So this is going to be our control group. This does give us something to compare to though, and they would have all of the same follow-ups and things like that that the treatment group would have. So that's an important part of the study. At the end of 1 year, 15% of those in the financial rewards group had quit smoking, while only 5% of those in the traditional group had quit. So this is our sample data, so we would represent this with p hat. The sample proportion for the treatment group was 0.15, and the sample proportion for the control group was 0.05. And if we want, we could use this information to fill in a two-way table like we saw before. So we have a total of 878 subjects, and it says that half were assigned to each group, so we'd have 439 who got financial incentives, 439 who got the control. And then to figure out what the counts should be within those groups, we have to use the sample proportions. So we have 439 people in the treatment group, and 15% of them quit smoking, so that would be 66 people. And if we subtract, that means that 373 people were not able to quit in that group. In the control group, again, we had 439 people, but this time only 5% quit, so that's 22. And if we subtract 417, we're not able to quit. So across the two groups, we had 88 people who successfully quit and 790 people who didn't. So clearly there's an association between the type of treatment you got and whether or not you quit in the sample, right? The people who got the financial incentive were much more likely to quit, but is it possible that this occurred just by chance and it's not something that would persist in a future study? There's a few different ways we can write our hypotheses. Let's just write them using symbols. So the null hypothesis would have an equal sign in it, just like it did before, and we could write this as pi for the treatment is equal to pi for the control, or maybe more commonly we write this as a difference, so we write pi treatment minus pi control equals 0. For the alternative, we have to look at the wording. So it says, does it provide convincing evidence that a financial incentive helps people quit? So we're sort of assuming that if it does anything, it has a positive effect, so it would be pi for the treatment is greater than pi for the control, or we can write it as a difference and again use the greater than sign. So remember, the reason that we're using pi is because we want a parameter and the response variable here is categorical. So we're interested in what's the long run probability of quitting in each group, right? We know what the sample proportion is, but we're trying to think about the long run proportion, which you can also call the probability. In the previous video, we used a simulation to test data like this. So why don't you take a second, pause the video, and think about how you would design a simulation in this context. And there's an outline given here for you. Okay, so first we need to decide which index cards to use. So when we do this, we're going to represent our response variable. So here, that's whether or not they successfully quit smoking. So we're going to use 88 and 790, and we're going to use that to represent the people who quit. That's the 88, and the people who didn't, and that's the 790. So you can actually do this more than one way, but the most consistent with what we've done in the past is to represent the response variable. Then we're putting all the cards together and shuffling them. We're not labeling them treatment or control. And so what we're doing at that point is assuming that we have the same probability of success, the equal probability of success in the two groups. So in the treatment and control groups. And that's our null hypothesis, right? We're assuming that the null hypothesis is true and that there's really no difference between these groups. Okay, then we're going to deal them into groups of size 439. And so that's to mimic the random assignment. And here we randomly assign them into equal sized groups. If we had done different sized groups in the original study, we would use different sized groups in the simulation. We just want them to match. This also helps you see why you need to do 88 and 790 when you're picking out your card colors, because you don't want to represent the same thing twice. We represented the response earlier. Now we're dealing into equal size groups to represent the explanatory. We need to calculate a summary statistic that summarizes the whole sample, and this does need to be a single number. So a lot of times people will say just like record the counts in each group or record the proportions in each group. But that doesn't really work because that gives us more than one number, and we want just one number to summarize the sample. So there's actually more than one option. We can do the difference in proportions. That's one way to summarize the sample. You could also use the relative risk and do a simulation with that. But whatever you choose, you're going to do lots of simulations, recording the simulated statistic each time, and that's going to give you the null distribution. Under certain conditions, we can skip the simulation and just use theory to tell us what values would occur by chance. So usually when you're using a theory-based approach, you start off by calculating a standardized statistic. In this case, we have categorical data, so this would be a z-statistic. And the general format is the same. It's the statistic minus the null value divided by the standard error. So here our statistic would be p hat t minus p hat c, the difference in our proportions. Our null value was 0, and then we would be dividing by the standard error. So in other situations, we have calculated this by hand when the formula wasn't too bad. In this case, the formula is a little bit complicated, so let's just let an applet do this for us. So I'm going to the theory-based inference applet, and I'm changing the scenario. We've used one proportion and one mean in the past. Here we're going to use two proportions. We put in our sample size, and it'll actually do the counts for you. So for example, if you put in 0.15, it'll tell you that the count would have to be 66. And we'll do the same thing over here, 439, 5% of them quit, so that's 22. And if we click calculate, it gives us our segmented bar graph. It also calculates the difference in the proportions, 0.15 minus 0.05 equals 0.1. So we want to know whether this is enough to be statistically significant. So we click test of significance. It's already set to 0. We do want to flip the sign around. So it's a greater than sign, and then click calculate. And we've got our z-statistic is 4.94, and our p-value is so small that it's estimated here to be close to 0. So our z-statistic was 4.94. And even though we didn't calculate the whole thing by hand, we do want to know what this represents. So it has the same basic interpretation as you've seen before for standardized statistics. Our sample statistic, which in this case was p hat t minus p hat c equals 0.1. Our sample statistic is 4.94 standard errors. Remember, we're putting it in terms of the standard errors when we're doing a standardized statistic. 4.94 standard errors above the null hypothesis value. So that's what we're comparing to. And in this case, the null hypothesis value is that the difference in the long run probabilities is 0. So before we even calculate anything, we know that 4.94 is really pretty extreme for a z-statistic. We expect z-statistics to fall between about -3 and 3 when the null hypothesis is true. But to show how we would use this, we would find our statistic out here on the edge. So this is our z, 4.94. And we would be shading to the right, since this is a one-sided test, everything that is more extreme than that, which is how we get that tiny p-value, right? It would be extremely unlikely to get a value of 4.94 or more extreme if the null hypothesis were actually true, meaning if financial incentive really made no difference, we would not expect to see results like this. So our conclusion would be that we have very strong evidence against the null. The null was not a good explanation, so very strong evidence against the null and for the alternative. And in this case, we would say very strong evidence that financial incentives, that was our treatment, that financial incentives improve the probability of quitting. So in other words, the probability of quitting is higher when they get the financial incentives, and that's compared to the control group. So this sounds like causal language, that something leads to improvement, but that's okay because we have a randomized experiment here, so it does support cause and effect conclusions. So the p-value tells us that we have very strong evidence that financial incentives make a difference, but it doesn't say how large that effect is. To answer that question, we need a confidence interval. So the basic form would be the same as you've seen in the past, a statistic plus or minus a multiplier times the standard error. In this case, our statistic would be the difference in proportions, p hat t minus p hat c, and our multiplier, because this is categorical data, would be z star, and our standard error would be the standard error of the difference. And instead of doing this by hand, let's just let the applet do it. We just click the box for confidence interval, and there's our 95% interval. So it goes from 0.0611 up to 0.1394. So why don't you take a second and try the interpretation yourself. Go ahead and write it down somewhere because I'm going to tell you the components that you need to check for. So the way I wrote it is we're 95% confident that financial incentives improve the probability of quitting by 0.0611 to 0.1394. So a couple things to look for in your interpretation. One, make sure that you clearly define the parameter. And this is actually important no matter what kind of confidence interval you're doing. It needs to be really clear what kind of parameter you're trying to estimate. So in this case, it would be a difference of proportions or probabilities. We can say probability because we're talking about the long run proportion. So even though I didn't use the words difference of proportions or probabilities in mine, notice that I am talking about the probability of quitting and saying that it has improved. So from that, you get that we're comparing two probabilities. Also make sure that the direction is really clear. So in this case, that means that the probability is higher with financial incentives. Make sure that it's clear which group is actually higher. So this is generally the problem when people write it just as a difference of proportions, is they don't necessarily tell me which way they're subtracting. So if you want to say we're 95% confident that the difference of proportions is between blank and blank, you also need to tell me that you're subtracting financial incentives minus control. And of course, if we're going to be doing a theory-based test, then we're going to need to have validity conditions. So this is a test for the difference in two proportions. We call that a two proportion z-test or a two proportion z-interval. And the validity conditions say that this test will work well when there are at least 10 expected successes and at least 10 expected failures per group. So this rule should sound familiar. It's very similar to what we've done earlier when we had categorical data, although the formula for the expected count is new in this chapter. So in a previous video, we said you calculate expected counts as the row total times the column total divided by the overall total. So let's do that for the first cell, the top left cell. We would do the row total, which is 88, times the column total, which is 439, and divide that by the overall total, 878, and that would give us a count of 44. So we can put 44 in here. We could use that formula 4 times to get the expected counts, or we can just subtract. So we would have the same thing in each group, and the expected number of failures would be 395 in each group. So here we see that our smallest expected count is 44, and we actually could have figured that out without even calculating them all. We could just look at the smallest row and the smallest column and put them together. So our smallest expected count was 44, which is still greater than 10. That's our cutoff. So here we would say that our sample size is large enough for a theory-based test. And I've just been letting the applet do the actual calculations for us because the calculation details are a little bit messy. I'm not going to ever ask you to calculate the standard error by hand, but I did want to show it to you just in case you're curious where these numbers are coming from. So if you look at the formula for the standard error, it does look pretty familiar. It looks like the same 1-for-1 proportion, except that we have two groups. So we basically have a separate component for the first group and the second group, and it's all summed together under the square root. So again, you're not going to have to do this by hand, it's just here if you're curious.